All right, let's jump right in. Have you ever wondered how two atoms can be the exact same element but somehow have different weights? I mean, it sounds kind of impossible, right? But it's this fundamental quirk of physics that honestly changes everything. Today, we're going to crack the code on isotopes.
So, here's the puzzle we're looking at. How can two atoms have the same name, sit in the very same spot on the periodic table, but one is heavier than the other? It feels like a total contradiction, but believe me, solving this is absolutely key to understanding a massive chunk of modern science.
Okay, to solve this little mystery, we've got to pop the hood and take a look inside the atom itself. Don't worry, this will be a quick refresher on the basics, but it's super important for everything that comes next. You can think of the atom as having a really clear division of labor. Right there in the center, in the nucleus, you've got the positive protons. Their job? They decide what the element is. Then you have the neutrons, which have no charge, they're neutral, and they just add mass. And then whizzing around the outside, you've got the negative electrons. And they're the ones in charge of all the chemical behavior. So it's a pretty neat system. 3 particles, each with a very specific job.
Now, this next part is absolutely crucial. An atom's proton count is, well, it's non-negotiable. It's like its fingerprint or its social security number. If an atom has 6 protons, it is always carbon. If it has 8, it's always oxygen. No exceptions. If you change that number, you've literally changed the element. So remember that. This rule is the foundation for everything.
All right, now that we've got that fundamental rule locked down, we can finally get to the twist in the story. If the number of protons is totally fixed, then where in the world does that mysterious difference in weight come from?
And here's the answer. Isotopes. That's the whole secret. An isotope is just a version of an element where the number of neutrons has changed. See? You can add a neutron or take one away, and because the proton number stays exactly the same, it's still the same element, it's just a slightly heavier or lighter version.
This little comparison here just lays it all out perfectly. Look at the what's the same column. The element name and most importantly, the number of protons, that's the atomic number, that stuff is locked in. It doesn't change. That's the atom's core identity. But then you look at the what's different column, and that's where you see the number of neutrons can change, and when that happens, it changes the total weight, which we call the mass number, and it can even mess with the atom's stability. Let's use a real-world example to make this super clear. Take carbon. Every single carbon atom in the universe has 6 protons, period. But its neutron count can be different. So carbon-12, the most common kind, has 6 neutrons, but carbon-13 has 7, and carbon-14 has 8. See? They're all still carbon because they all have 6 protons, but they have different mass numbers, which, by the way, is just the protons and neutrons added together. You know, there's a great analogy for this. Think of it like a bunch of identical backpacks. The backpack itself is the element, defined by the protons, so let's say it's a carbon backpack. That part never changes. But the number of books you put inside, those are the neutrons, that can be different. So some backpacks are just heavier than others, even though they're all the same kind of backpack. Simple, right?
Okay, but this difference in weight isn't just some fun little trivia fact. No, it has huge consequences. Some isotopes, like our friend carbon-12, have a nice balanced nucleus, and they're perfectly stable. They just hang out. But others, like carbon-14, are unstable. We call them radioactive. All those extra neutrons kind of upset the delicate balance in the nucleus, and that makes the whole thing unsteady. So eventually, it'll break down or decay and release a bunch of energy when it does.
So a tiny little particle changes deep inside an atom's core. You might be thinking, okay, why should I care? Well, because it turns out that this tiny, tiny difference has massive, world-changing implications.
I mean, the real-world applications are just incredible. That predictable decay of carbon-14, that's what lets us do carbon dating and figure out how old ancient fossils are. In medicine, radioactive isotopes are the magic behind things like PET scans that help doctors diagnose diseases, and they can even be used to target and destroy cancer cells. We use them in environmental science to track pollution, to see where water is moving, and of course, certain isotopes of uranium are what power our nuclear energy plants. I mean, the impact is just staggering.
So let's bring it all home and get to the final takeaway here. We started with what seemed like a simple mystery, right? And the solution ended up unlocking this whole new way of understanding the atom. Really, it all boils down to this super simple 2-step idea. If you remember anything from this, remember this. Step 1, same element always means the same number of protons. Step 2, different mass means a different number of neutrons. That's it. That is the core idea of an isotope in a nutshell.
And that right there is why this all matters so much. A single neutron, one more or one less, is what helps us uncover the age of the dinosaurs, diagnose life-threatening diseases, and power our entire cities. It's just a perfect reminder that sometimes even the smallest particles can tell the biggest stories.